Okay, good morning. Let's start our section of today of time physics workshop. I just want to present you Alexander Smith, assistant professor of physics at St. Anselm College. As an undergraduate, he studied at the University of Waterloo and then moved to the University of Toronto to complete a Master of Science. He then enrolled in a Coursera program at the University of Waterloo and Macquarie University, earning a doctorate degree from both institutions. He joined the Dartmouth community as a junior fellow in the Society of Fellows in 2017 and was awarded an NSERC postdoctoral fellowship to work in the area of relativistic quantum information. In 2020, he began assistant professorship at St. Anselm College. His work takes an information theoretical approach to investigating questions at the intersections of quantum theory and gravitational physics. His research interests includes quantum information, science, quantum field theory on curved space-times, interferometric tests of the equivalence principle, and the relational formulations of quantum mechanics. Thank you for coming here, Alex, and the floor is yours.
Oh, thank you very much. And thank you to the organizers for inviting me and giving me this chance to share some work. This is based on several papers with my colleagues I've had the pleasure of working with. Mehdi Amadi at the University of Santa Clara, Andrzej Dragan, and Kasper Debski at the University of Warsaw, Piotr Golczewski at ETH Zurich, Philip Hoon at the Okinawa Institute of Technology, Max Locke in Vienna, and Andre Russo, who just graduated from UCL. So what I want to talk to you about today is going to be 4 parts to the topic, or to my talk, sorry. The first, I want to give you a quantum description of clocks and what we actually mean by measuring time in quantum mechanics. And then I'm going to use these clocks to talk about relational formulation of quantum dynamics, where we start with the Hamiltonian constraint, very inspired by general relativity, and talk about how we can use these clocks here to get a relational notion of dynamics using a clock that's internal to the system we're investigating. I'll then present 2 different generalizations of this relational quantum dynamics. One, when the clock is interacting with the system whose dynamics it's trying to track. And this is important because that's what happens in the Hamiltonian constraint and general relativity. And then a generalization to field theory. And then finally, I'll use the formalism that I've developed to talk about a new effect that we call quantum time dilation. The idea is, what would be the kinematical time dilation a clock would experience if it's moving in a superposition of 2 different speeds. And you can actually show that you get a quantum interference effect in the proper time that would measure using this quantum description of clock. So let me begin. Starting back with what is time, going back to Einstein, and this nice essay he wrote in 1949, he says, time is considered measurable by a clock of negligible spatial extent. The time of an event taking place at a point is then defined as the time shown on the clock simultaneous with the event. So going back to the questions Nadja asked at the very beginning, what is time? Here's Einstein's answer. Yeah, time is what's measured by a clock. And it was Percy Bridgman. He was originally a chemist and then became a philosopher and wrote this influential book, The Logic of Modern Physics. He says Einstein's doing more than just defining time here. He's actually saying that what Einstein's doing is actually adopting a new point of view as to what the concepts in physics should be. He says Einstein, in seizing on the act of the observer as the essence of the situation, is actually adopting a new point of view as to what the concepts of physics should be, namely the operational view. In general, we mean by any concept nothing more than a set of operations. The concept is synonymous with the corresponding set of operations. So for Einstein in relativity, he's saying, okay, we have this idea of clocks, and time is what these clocks measure, and that's it. This is different than Newton, how Newton began in Principia, saying this absolute true and mathematical time flows equitably without regard to anything external. There, Newton's positing that there's this thing out there a priori, and it doesn't really matter how we go about measuring it. So this is a different approach. So how do we import this in quantum mechanics? Well, Pauli thought about this, and in his book, he wrote this little footnote. And he says, I mean, this equation here, the Schrodinger equation, that's the only place that time appears in the quantum theory. And he says the following. He says in the older literature in quantum mechanics, we find this commutation relation between the Hamiltonian h and t. Namely, we want the Hamiltonian to generate translations in t, and so it better satisfy this commutation relation. But then he points out that it is generally not possible, however, to construct a Hermitian operator as a function of p and q, which satisfies this equation. This is because H possesses continuously all eigenvalues from minus infinity to plus infinity, and any physical Hamiltonian ought to be bounded from below, and furthermore, some have discrete spectrum as well. So the conclusion he reaches is we therefore conclude that the introduction of an operator T is basically forbidden, and T must necessarily be considered an ordinary classical number. This is where, the folklore, time is a parameter in quantum mechanics. This is really strange, right? Because we measure time all the time, and somehow quantum theory can't incorporate it consistently into its description. So I think Pauli's fundamentally wrong here. I think there's a more general class of observables that I'll introduce to you that allow us to incorporate the measurement of time. And so I think it's kind of a red herring just to say that time is a parameter or somehow it's not measurable in quantum theory because we can't construct the self-adjoint operator. I'd like to show you a way in which we can talk about the measurement of time. So what is a clock? Okay, or a temporal reference frame if you like. It's defined by this quadruple here. So a clock, it's a physical system. We describe it by a Hilbert space. Okay, it's going to have some Hamiltonian. It's going to govern its evolution. There's going to be some fiducial state we prepare the clock in. I'll call that rho c. And then there's going to be some time observable, TC. Okay, that's not necessarily a self-adjoint operator. In some cases, it can be, but more generally, it's going to be a different object. And what do we expect of a clock, right? Well, if we consider the initial state of our clock to be rho c, well, then it just evolves forward in time under the evolution generated by the Hamiltonian. So that at some later time, we get rho c of tau, okay? And this tau is a parameter. It's going to be in some set that's ultimately going to be a group. And what do we want of this time observable? What properties should it have? Well, there's two, right? On average, when we measure this time observable TC, given the states rho c of tau, on average, it should return the time tau, right? That's what it would mean for it to be a time observable. And second, the variance in a measurement of this time observable should be independent of what tau is, right? When we go to measure our clock on the wall, right, we have some uncertainty associated with it, but it's independent of what time the clock is showing. So it turns out that these two conditions uniquely specify what this time observable should be. And so the object that this time observable is going to be described by is a positive operator value measure, or POVM. So, yeah.
So Pauli was wrong because he was not considering POVM operators to describe.
Yes, this is my take on that. And there's others in the literature too, so I'm not as radical as maybe I'm sounding, but yeah. So the point is that we have to appeal to a more general description of observable in quantum. To talk about time. Mm-hmm. So, okay, what is a POVM? Well, it's a map from this set G to the space of effect operators on the Hilbert space. Okay, so let me tell you what these effect operators are. For simplicity, we can consider for every instant of time, tau, we can construct this projection operator that's defined in terms of these things I'm going to call clock states. Right? And then we demand that these effect operators satisfy some properties. They're positive, they add nicely, and they're normalized in the sense that they sum up. If you average over all times or integrate over all times tau, you get an identity. And the point of these three properties are so that when you ask, what's the probability of the clock reading a particular time tau, given it's in the state rho, you can just use the usual Born rule. So basically, those three properties guarantee you're going to get a well-defined probability.
Sure, what's C here? What's the C standing for?
For the clock. Yes.
So the identity of the clock is that on the 3 is the IC is.
Yes. So when I sum up over all of the possible T, I get an identity.
Well, just the identity. I don't understand the subscript to the I.
I see. So this is the identity on the clock Hilbert space.
Okay.
Yeah. There's gonna be more Hilbert spaces coming later, so I wanted to leave. Okay. So this is the general properties of a POVM, but what makes it special about a time observable is that these clock states satisfy a particular covariance property. Namely, the different clock states, tau, are connected to one another by the time evolution group generated by the clock Hamiltonian. So this leads to this notion of a covariant POVM. And these are much more general. You can talk about covariant POVMs with respect to more general groups. But these were first started to be discussed in the context of quantum metrology in the 80s by Holovo and others. And so if your clock states satisfy this property, then it's going to satisfy those previous two properties I showed on the last slide. Namely that the average value read by the clock is going to correspond to tau, and its variance is going to be independent of the value of the clock it's reading. So let me just give you a few examples of this time observable. So the simplest clock you might imagine is just a particle moving along the real axes, okay, in one direction. The Hilbert space there is L2 of R. Okay, we can imagine it's Hamiltonian just being the momentum operator. And then the clock states are going to be connected to one another by the group generated by the Hamiltonian. In this case, it's the translation group. So you can think of these clock states as different position eigenstates of the particle. So really what you're doing here is the particle is just moving at a uniform speed along in one dimension, and you're measuring its position, and that position is going to be this covariant time observable associated with such a clock. Okay, and in this case, these clock states are all actually orthogonal to one another, and that allows you to associate with them a self-adjoint operator, namely the position operator. But this construction is more general. A different type of time observable you could look at is a qubit. So you might imagine your clock Hilbert space is just C2, okay? And then your Hamiltonian, maybe it's a spin-one half particle in a magnetic field oriented along the Z axis, is just going to be proportional to sigma Z. So in this case, you can pick a clock state. The clock states tau are going to correspond to points on the equator of the Box sphere. And so basically what's going to happen is the evolution generated by that Hamiltonian is going to sweep out the equator of the Bloch sphere, and those are going to be your clock states. And if you construct those effect operators, they integrate to the identity, so they define a POVM with these effect operators here. But these clock states are not orthogonal anymore, right? And so in general, you can't associate a self-adjoint operator to this POVM. Yep.
So it is still true, though, that the self-adjoint operator that are associated with the clock does not have the appropriate computation relations with the energy.
This will in this case because it's just X and P.
And the Hamiltonian is P.
And then the Hamiltonian, you say, okay, it's unphysical, it's unbounded from below, etc. So this is why we need to go to this more general, because this Hamiltonian is from below. Yeah.
Do you have something to say about the precision of your clock?
Yes, I will state an uncertainty relation. Yes,
Okay.
that's good. Just 2 slides. You're ahead. Yeah. Okay. Are there any questions so far? I'm happy to. Okay. Leonardo asked me over lunch about if I had another yesterday, so I did some homework. I added 2 more slides to give another example, but he's not here at the moment, so maybe I will skip these because it's a little bit more complicated. But another Hamiltonian you might have is basically a p squared Hamiltonian. Okay, this is like the free particle. P squared appears in all sorts of different systems, harmonic oscillator and different models of cosmology, relativistic particle. So the point is here, even in this case, right, this Hamiltonian is bounded from below. You can't find a self-adjoint time operator, but you can go through and construct a covariant POVM. So maybe just quickly, what you might do is classically is you might say, okay, well, here's Hamilton's equations. Okay, so I want to find out what's the position of the particle. Okay, I use Hamilton's equations. I can solve this equation, and then I can solve for t as x over p, right? And then I can try and quantize that operator, and I get something that looks like this. And so this operator here, it does satisfy the correct canonical commutation relations. However, it's not self-adjoint. Okay. What you can do is you can construct these clock states. Analogous, there's two classes of them. They're a little bit more complicated, expressed in the momentum basis here. But the point is, the connection with that operator on the previous slide is that it's the first moment of these POVMs. So that's what you would measure on average. Okay, so I guess, I mean, here is that this construction of covariant POVMs applies to all sorts of different Hamiltons. Okay. So coming to this idea of an uncertainty relation, what is also special about these covariant POVMs is that they're optimal. Yeah. Okay, so you might say, okay, that's nice. You know, maybe I can do better and minimize the variance or something like this. Maybe there's some other observables that I could construct. But it turns out that in this estimation problem, so say you have some state rho C of tau, where we say this parameter tau, in this case it's time, is unitarily encoded in this initial state of our clock. And you ask, what's the best measurement, or what's the lowest possible uncertainty in a measurement of that parameter tau? You find that it's bounded below by what's called the Kramer-Rao bound. That's 1 over the square root of the Fisher information, for those of you who are familiar with that concept. But then that leads also the Hellstrom-Holovo lower bound, which means this is lower bounded by 1 over the uncertainty in the generator of, in this case, the clock Hamiltonian. And it turns out that these bounds are saturated by covariant POVMs in that sense. So the best you can do, the best time observable you can construct that saturates this is exactly those covariant POVMs that I'm telling you. So this also spits them out as sort of a unique notion of what a time observable is. Okay. All right, so that's what a time, we measure time in quantum mechanics, how we describe it mathematically. That's what a clock is. And I want to use those clocks to talk about relational quantum dynamics. So the big idea here is we're going to have some Hamiltonian constraint, CH, and we're going to demand that the physical states of our theory are annihilated by that constraint. And so the question is then, how do we recover an internal notion of dynamics? And so I want to use these covariant POVMs to do that. So, okay, why should you be interested in this problem? Well, if we look at general relativity, okay, and we try and formulate it in its canonical form, and we pick some canonical variables like the 3 metric and its conjugate momentum, and we write down the Hamiltonian, we find exactly that it's constrained to vanish. It equals 0. So here we have a kinetic term, a potential term, and then some coupling between the 3 geometry and the stress energy of the matter degrees of freedom. And so if you try and quantize this theory, maybe you follow the Dirac prescription, you're going to impose that the physical states, how do you impose this constraint in the quantum theory? You're going to demand that the physical states of your theory psi that describe both the 3 geometry and the matter are annihilated by this constraint. And then maybe you want to impose some dynamics. So you postulate the Schrodinger equation.
Sorry, what's log G, A, B, C, D?
This is the Witt metric on superspace. So it's basically, this is like a kinetic term.
Okay, what's this Hamiltonian? I mean, does it come from
Yeah, this is AVM.
Okay.
Cool. And so we might postulate the dynamics, say, okay, well, the Hamiltonian is supposed to generate time evolution, but if our physical states are constrained to vanish, they don't actually evolve in time, and you get one aspect of what's known as the problem of time, that your physical states are frozen. And so the question is, how do you recover this notion of dynamics that we're all familiar with? So instead of looking at general relativity, it's a little bit complicated. Let's look at a simpler system. And I want to imagine we have some theory of some system S, okay? And how would we analyze it, at least classically, right? Well, we write down some Lagrangian, we carry out the canonical analysis, and we get Hamilton's equations. But we can also describe the theory with another action, where instead of imagining there's this external time, we might imagine that we have some clock in some system, and our clock is going to be described by the configuration variable t, and we might write down some action for that configuration variable. Yeah? And if we choose that Lagrangian, and here now let me just say tau is an arbitrary parameter that we're defining our action with. But if we choose this Lagrangian correctly, right, we find that it's actually equivalent to this action here. So the theories are going to be described, or are going to be the same that result. However, the difference is in this action, both the configuration variable of the system and the configuration variable of our clock are both treated dynamically. They both appear in the Lagrangian. And when you do the canonical analysis here, you get a Hamiltonian constraint, similar to what appears in general relativity. So in this case, the Hamiltonian, what you find, just doing the Hamiltonian analysis, is that you have a constraint, CH, that's the momentum associated with the clock, canonically conjugate to the position variable of the clock, plus the Hamiltonian of the system is constrained to position. So, okay, so then we can try and quantize this theory, just like I showed you how we might do with the Dirac prescription with general relativity on the previous slide. And so what you say is that, okay, well, I'm going to promote my constraint to an operator and demand that the physical states of the clock in the system are annihilated by this constraint. So here I have this momentum operator acting on a clock Hilbert space, and then the Hamiltonian acting on a system Hilbert space, and I'm going to demand that the physical states of the clock in the system are annihilated by this constraint. And then you might say, okay, well, that's fine, but that's a very different constraint than general relativity. Namely, we have the clock Hamiltonian, the momentum is appearing linearly there. So what you might do is then, okay, well, let's replace PC with a more general clock Hamiltonian. This is fine. And then you might say, well, okay, if I look at the Hamiltonian constraint in GR, there was this interaction term, right? Between maybe our system is the geometry of space, and then our clock is going to be made out of some matter degrees of freedom. So in general, there could be some interaction that couples the clock and the system. So this would be the most general constraint I could consider. For now, I'm going to ignore this interaction, but I'll come back to it in a few slides.
Sorry,
Yeah.
you are not quantizing the space-time. So you're assuming a quantum operator describing your clock coupled to a classical degrees of freedom. Am I right?
Yeah, I mean, I would think of it as I have sort of a quantum mechanical system. I have a clock. It could be described by a particular Hilbert space, L2 of R. So maybe this is a particle in space.
Okay,
but
you're not quantizing the metric of your
no. I'm trying to motivate this constraint by appealing to saying something similar happens in general.
Okay.
Just curiosity, I see that you renamed PC to HC,
Yes.
which looks like Hamiltonian. Are you changing the concept?
Yeah, so I wouldn't say changing the concept. I would say in the simple example I showed you, this is the example of what's called the parameterized particle. There, when you do that, you get a Hamiltonian constraint, and that Hamiltonian constraint is rather special because the momentum of the clock appears linearly in it. And I'm saying, well, using these covariant, using these covariant POVMs, you can consider a more general clock Hamiltonian that isn't the momentum operator. And this is important, right? Because physical Hamiltonians ought to be bounded from below. And even in this one, right, this is P squared, right? So it's again, in general relativity, the momentum isn't appearing linearly either. Good. Okay, so this leads me to this page, Wooter's formalism of how to go from a Hamiltonian constraint to a Schrodinger equation or a relational dynamics. So the idea is we have this Hamiltonian constraint I showed you without an interaction, HC plus HS. Okay, and our physical states of the clock in the system are annihilated by this constraint. And then what we're going to do is we're going to pick a time observable that's described by a POVM. So here are the effect operators. They're covariant with respect to the group generated by HC. And then maybe there's some system observable that we're interested in. Okay, and I can describe it as well by a set of effect operators. So maybe I'm measuring the spin of an atom. Okay, and I have spin up and spin down. So A would be plus 1/2 and minus 1/2.
Is it important that there is a group that is generated by this?
Yes, maybe you're thinking of like more general things like, yeah. At least for the construction of these covariant POVMs, it has only been looked at for groups. So I think that's interesting to ask if there's more general groupoids and these
Yeah,
sorts of
exactly.
things, yeah. Okay, so then this is the fundamental insight of Page and Wooters, is they say, what is dynamics about? It's about conditional probabilities. It's about what is my system doing when the clock is reading a particular time. Yeah. So they say, okay, what's the probability that maybe I have spin up when the clock reads the time t? And then they just use the expression for conditional probabilities in quantum mechanics. And what they find is the following, is that if you define a conditional state of the system where you take one of these clock states and you project the physical state onto one in which the clock is reading the time t, you find that this conditional probability is given by this probability amplitude squared. And furthermore, this state here, because of the covariant property of the POVM, satisfies the Schrodinger equation. So this is, I think this is really amazing. This got me hooked on this topic, is that from just conditional probabilities, you can recover a notion of dynamics and recover the Schrodinger.
Could you say that again? I mean,
Yeah.
trying to find out how the probability yields an equation of motion. I mean,
Okay, so basically, I can rewrite, if I do a bit of algebra, okay, I can rewrite this conditional probability as this probability amplitude squared, which is what we would appear in sort of orthodox formulations of quantum mechanics. And the point is to define this conditional state of the system, we take our physical state which satisfies the constraint and project it onto one in which the clock reads the time t. And then you can just ask, well, what's its time derivative with respect to t? And you can show, using the constraint and the covariant property I introduced before, that you get the Schrodinger equation. So I want to say a few words on this. Why formulate quantum theory in this way?
So just one.
Yep.
In this proof, in the proof of this last equation, I'm sorry.
Sorry, yeah.
So do you said you use the constraint, you use
Yes.
that, so you're using that okay, all right.
You use the constraint and then the covariant property of the time observed. Yeah. Yeah. So, okay, why formulate quantum theory in this way? It's because dynamics now, you don't have to postulate the Schrodinger equation independently of the kinematical structure or the measurement theory of the quantum mechanics. It arises just by asking about conditional probabilities in the Born rule. Yeah. So I really like this. This is a follow-up essay that Bill Wooters wrote after. He says, one motivation for this considering such a condensation of history, he's referring to the physical state there, is the desire for economy as regards to the number of basic elements of the theory. Quantum correlations are an integral part of quantum theory already, so one is not adding a new element to the theory, and yet an old element, time, is being eliminated, becoming a secondary, even approximate.
Of course, I mean, this would also apply if you had certain properties, well, I was going to say space, but then you wouldn't associate a Hamiltonian with.
You might have a momentum constraint, and then you could ask, if I have a quantum reference frame associated with position, and I can ask, what does this system look like relative to the origin of my lab at this location? You would get, the translation group would come out instead of the time evolution group. Right.
Well, just to clarify the citation, it's meant that, could you put it back?
Yep.
The very end, no, the citation of the.
Wooters, yes.
Yeah. Wooters. Time being eliminated, but in the equation above, it's not eliminated yet, is it?
Well, I think what he's saying is that usually, at least in orthodox formulations of quantum mechanics, we postulate independently the measurement axioms. We say, okay, the Born rule, the collapse of the wave function. I'll say a little bit more about this on the next slide. And then we also postulate unitary dynamics, or the Schrodinger equation. And so these are independent. And what he's saying here is that just from the Born rule and conditional probabilities, the measurement theory in quantum mechanics, I can recover a notion of dynamics. So I can derive in some sense from the measurement theory the Schrodinger equation.
But then time is being eliminated. It did, in the equation above that's written there is still a time element, right? So for now, I mean,
It's a state of, it's a state of the system, it's a parameter describing the state of.
okay, T is the state of the system of the clock, right? That's what I mean.
Yeah, it's describing a particular type of observable you might measure on the system.
Yeah,
That you
and a
guys-
special
yeah.
system that is always accompanying the system you're observing.
Yes,
The clock is a system,
yes,
so.
treated on equal footing and dynamical in the same sense that the system you're interested
So
in.
that's not because, that's why it's not the old element time. It's a
Yes.
new way to see the way you mark simultaneity.
It's not an external time, it's not an external time.
Maybe this is a way.
The
of-
time is inside the system.
Yes, yes, this is a good
Okay.
message.
Yeah, that's what I mean.
Well,
Yeah.
sorry, just a comment, but still, you are making quantum mechanics on a background space-time,
Yes,
right? So, and before all this, you have to define your space-time, and you have to have a time, otherwise you cannot, not even begin this. So what I would
I
say,
will, okay.
let me try to rephrase
Mm-hmm,
this statement in another way.
mm-hmm,
So, but after all, in order to do physics, you have to have something to measure that concept that space-times require, namely time. So as Einstein said, time is what clocks measure.
yes,
And we are realizing a clock and say, look, I'm going to parameterize my equations by the reading of my quantum mechanical clock.
mm-hmm,
But you are not eliminating time. Time is not secondary. Actually, it's primary in the sense that you are making all your physics in space-time physics. But you're realizing a clock where the measuring of your display is connected with this concept of time. Do you agree with that?
not entirely. I agree, I'm looking at mechanical systems that we usually think of embedded in some background space, but I could in principle do this with just two qubits, just two abstract qubits and two Hilbert spaces.
It's
Yeah,
just
and not
configuration
multiple.
space, you don't need, so if you take the weight equation, and so on, the states, you just need the configuration space or there is no time there. Just a spatial configuration space of instantaneous configurations.
Well, your qubits are somewhere. They are in the space-time,
Well,
right?
no,
Yeah,
I mean,
you
I can
are-
describe them without different states of qubits irrespectively of time.
I think that the approach here is a bit different from space-time. What is being said is that there's no gravity here. Space-time describes gravity, right? So here you're saying there is no gravity here. It's just a system, and for now,
Uh-huh.
it's this vacuum. I mean, there's no gravity, so we don't need to bother about space-time. So we have a system with no gravity. So we don't need for now to worry about how gravity.
You can
No, I'm not
describe
talking-
gravity in a 3+1, and it would be the same thing, you'd have just spatial configurations of three-dimensional metrics.
Yeah, so when I look at,
Yeah, but when,
maybe this is the
when,
connection.
if you think about describing in 3 dimensions plus one.
No, plus one.
Okay, no plus one, that's what I'm saying,
Yes,
yeah. But
yes,
if you don't need to worry about space-time, if you don't have gravity, okay, at all. I'm just saying that for us to
uh-huh.
not worry about background space-time here.
I mean, if I wanted to talk about gravity, the way I would do it is I would formulate it in terms of this Hamiltonian constraint. And then maybe my clock is made out of matter degrees of freedom, rho, okay? And then maybe the dynamics I'm interested in is the unfolding of 3 geometries. And that would be described by the configuration variable of the 3 metric. Okay, and I'll just maybe mention that this constraint, usually the way we learn it is we do the ADM formalism, but there's other ways to motivate that constraint that don't rely a priori on a 3
That's
plus
why
1
I'm saying
space.
there's no gravity, because the time you're studying here,
Mhm.
it's a clock that is not influenced by gravity. It just goes, have straight line, so on. When you said it goes in a straight line, is that because you don't have any force action on it? So that's why I think we could say there's no gravity. Or any other force action on your clock.
I mean, there's a
It
Hamiltonian,
doesn't, but you.
and so,
your clock need- sorry.
yeah,
It
yeah.
just needs to go straight line, or even when it's moving this way, it must go in a way, steady and repetitive. So there's no force influencing that. I don't, I
mean,
mean, maybe it could.
We can talk after, yeah. But I mean, the way I'm describing my clock is that quadruple, and that's the complete description. So I have a Hilbert space, I have a Hamiltonian, I have an initial state, I prepare it, and then I have this particular covariant POVM that I'm calling a time observer.
But actually, and it must be a system that's always marking the good time for you. Otherwise, it's not a clock for the observer.
No, what I mean by a good time is those covariant time observables, that they satisfy that group theoretic property that
Yeah,
they're
but physically, it
covariant.
must be
Um,
to become a clock for the observer.
So, for example, I could have a particle on a line, I prepared some initial state moving and I can measure its position. Or if I had a qubit, I could measure where it is on the equator of the Bloch sphere.
Do you agree that it has to have a steady motion, a constant spinning motion, or something that?
No, because
It doesn't need to walk.
because I can have a clock, I could drop this, okay, it's accelerating, right? It's not steady motion, there's a force on it, but I can still use its position as a clock. My equations just wouldn't look as simple.
But I have to know that so I can understand how it's measuring time, right? What a tick is, what a second, whatever it is, right?
It's
I
defined,
understand.
it is defined, there's no other notion of time, that the motion is defining the time.
Yeah, so
there's
I
no
define
notion-
that way.
Yeah, there's no
Okay,
notion
that's
with
okay.
respect which must be uniform.
As long as I define, so that this is a clock, this is good for me, right?
Okay, yes,
That's the
that
point.
definition, yeah.
Yeah, that's
Yes.
because you started with a straight line and that's just to make sure we're on the same page.
I would just say, that I started with a Hamiltonian that generates a group, a one-dimensional group. That's maybe how I would say.
Alexander, did you already say what POVM stands for?
Yeah.
Positive operator value measure.
Thank
Yes.
you. Right.
Sorry.
Yeah,
Okay. Good, all right. So, okay, I want to come back to this point of time being eliminated. This is a very nice picture from Roger Penrose's book, The Road to Reality. And he talks about the dynamics in quantum theory as this jump between these two processes. He says this alteration between two completely different looking procedures would appear to be a distinctly off type of way for a universe to behave. So he's talking about, we have some unitary evolution, then some measurement and some collapse of the wave function, whatever that is, and then some unitary.
an R when it reduction for R. Did you take it from his book?
Yes, yeah, it might have been R. I probably put M for measurement
Oh.
because this made more sense to
It
me.
was an R.
Yeah, good memory. But when we have a physical state and we just look at conditional probabilities, we never have to talk about the physical state collapsing. It just is what it is. And we get dynamics from asking conditional probabilities, and then we can define, if it makes us feel good, this conditional state, right? And talk about what it is after measurement. But the point I just want to emphasize is that I really don't see this tension between two dynamics happening here. All we have is the physical state, which is what it is. It's independent of time. And then if we want to talk about dynamics, we just have to ask about conditional probability.
There's something about, so Roger no longer believes that was causing a problem for the interpretation of quantum theory.
Okay, I'm not familiar with.
I don't know if you wrote about it, you just told me that, so for those collapses, that was what led him to postulate that the theories need to be irreversible.
No, we're already quite late because we already had.
Sorry, yeah, go on.
At the end.
Yeah, I should check the time. Okay, so maybe sometimes in the literature it's been said that there's this very nice picture from this paper by Javet and Lloyd and McCone, where time sort of comes from entanglement. This statement, and this got, I think, a lot of people in the quantum information community excited. I just think it needs to be just a little careful about what we're saying is entangled in some sense. So we could take our physical state, right? I mean, sorry, let me just back up. These conditional probabilities, there has to be correlations between what the clock and the system is doing. And what we can do, we can act on the physical state with an identity operator and then expand it basically as this superposition over all instances of time, where we have a state of the clock and the state of the system at some time t. But the point is, and I can say more maybe in the question period, that this is an entangled state, but it's entangled with respect to what we call the kinematical Hilbert space, the Hilbert space before we impose the constraints. And it's not always clear whether that entanglement there will become physical, or that tensor product structure will survive on the physical Hilbert space. So yes, you can write it as this big superposition over different instances of time. And you can imagine this state as this block universe, and when we condition, we're picking out different slices. But yeah, I just wanted to mention that. I know there's maybe a poster by, I think, Tiago, talking about some of this entanglement. Okay, so what happened? Okay, I've just told you a very nice, what I think is a very nice story, maybe you don't, about how we recover a relational notion of dynamics. This was done all the way in the early 80s, in 1983. So why didn't this approach become popular? I think it was pretty heavily criticized right off the bat by Karl Kukash. So he's talking to Don Page in these quotes that I'm quoting here at a conference, and he says, what's wrong with this approach? He says, you never apply the conditional probability formula to answering the fundamental dynamical question. Namely, if one finds the particle at A when the time is t1, what is the probability of finding it at B at time t2? By your formula that the conditional probability differs from 0, if t1 is equal to t2 and the overlap between A and B is not equal to 0. So what is he saying here? If I have some conditional state of my system, okay, and I make a measurement at time t1, I'm going to have a projector associated with that measurement, associated with the clock reading t1 and getting outcome A. And then I would have some collapse of this conditional state to A. And then I would make another measurement at t2, maybe some other observable B, and I would get the state B. He says, okay, if I apply this, what he first says, okay, what is dynamics really about? It's about this two-time conditional probability. If I have some initial A when t1, what's the probability of B when t2? And he says, well, really, you should be using this formula for the conditional probability. And if you go through the algebra, I won't bore you with it, but you get a square of the delta function here. This is only non-zero, and it diverges when t2 is equal to t1. But the important point is that it's not equal to the propagator between A and B. That is what you would normally expect, namely the U of S, the unitary generated by the system Hamilton. So then he says, in brief, your interpretation prohibits the time to flow and the system to move. For me, this virtually amounts to a reductio ad absurdum of the conditional probability proposal. And then Don comes back, he says, only quantities at a single instant of time are directly accessible, and so one cannot directly test the two-time probability you discuss. One could instead, at one time, test the conditional probability that the particle is at B, given that the time is t2, and that at this time there is a record indicating that the particle was at A at the time t1. So what he's saying is we never actually probe those two-time probabilities you mentioned. It's that we have memories of the past, they're encoded in the present and in some register. And so the correct probabilities to consider are these one-time ones that Don had and Wooders had considered. Okay, and then Kukash fires back. He says, Don, you are the first person I met who simultaneously believes in the existence of many worlds and is a solipsist of an instant. Okay, and then Don goes on and I believe that different instances, different clock times are actually examples of different worlds. They all exist. So when he says different worlds, that superposition state I showed you, right? The different branches would be these different worlds. They all exist, but each observation and its associated conditional probability occurs at one single time. We can only directly observe and be aware of the world and the time in and at which we exist through the correlations and memories and other structures we observe in one world, given indirect evidence of other worlds and other clock times in the full quantum state of the universe, the physical state.
May I ask you
Yes.
something? Why can you go back to the criticism, Kukash? Criticism? Okay.
Yeah.
My question is,
Oh, one more.
the previous one. Yeah, that one.
Uh-huh.
So if we consider, if we consider what you said till now as a realization of the quantum clock, why can't we resolve this criticism by saying that you are going to use an infinite number of clocks in such a way that one is going to measure the ascribe a time instant
Mhm.
A, and use another one prepared equally as the first one to measure the instant of time at B.
Okay, you can do something sort of like this. I'll talk about this in a few slides where you basically store the time read by the clock in a memory in an auxiliary system,
Okay,
and you can recover. So maybe this will, but I'm going to point out there's actually two ways to do it. How much time do I have left? Maybe
I can have 15 minutes.
15 minutes left? Okay.
okay.
All right, so then, well, okay, if I only have 15 minutes left, let me skip a few things. This is the history of the proposal. Maybe I just point out that the original paper by Page and Wouters was 83. And Kukash's criticisms really came around the early 1990s. And I think this approach was superseded by these partial and complete observables of Rovelli, these evolving constants of motion, which came in the mid 80s. But then there was sort of this history where it wasn't taken, Kukash's criticisms sort of held weight. And then they started to be addressed by Dolby and Giovanni Lloyd and McComb. And then me and my colleagues addressed Kukash's criticisms in a different way as well. So I only have 15 minutes left, so maybe I'm going to skip a little bit of this. Yeah.
So you started at 9 o'clock, right?
We started a little after.
I did
but-
after.
Yeah, I think you could have, since we're interrupting you, so
Okay.
maybe we could go up to 10:15 and then we discuss in coffee. break.
Okay. All right. This is
We're
good.
gonna have
Then you have 25.
25.
25 minutes. Okay. All right. Okay. So maybe just quickly, one way to resolve this is to claim that Kukash was actually computing that conditional probability incorrectly. And that what one should do is construct what are called complete or relational observables. And this is the idea of finding a gauge invariant observable, one that commutes with the constraint that describes what the system is doing, maybe the height of a ball when the clock is reading a particular time. Okay, and there's a whole procedure to go about. I will skip this just in the interest of time for computing these, but there's a well-defined procedure for computing these, and you can then quantize these using covariant POVMs, where you quantize this time observable T there using a covariant POVM, and you get basically this group average over the group generated by the constraint of the clock reading a particular time and the observable you're interested in that. Okay, so all I want to just point out here is that you can construct these complete observables that correspond to when you measure them, what the system is doing when the clock reads a particular time.
When you compute the conditional probabilities, it's taking the conditional is to the history that you've reported, or that
You're using the physical state that satisfies the constraint.
and that is going to be used to report what the past that you're trying to take into account.
Yes, in one approach to answering Kukash's criticism, yes.
Okay, is there a physical mechanism to report that?
Yes, I'll show that in a second. Okay, so basically what you can show, okay, is that these conditional probabilities of that Page and Wouters were looking at to get the relational dynamics in the conditional state is the same as the expectation value of those physical observables I told you. And then to compute the two-time probabilities that Kukash was really interested in is you actually need to use these complete observables and the standard conditional probability with those. Kukash wasn't doing this when he made his argument. Okay? So I agree, I went kind of fast here, but you recover the right propagator. And I'm happy to say more about this in the coffee break. But the point is that you can overcome Kukash's criticisms in the way that he had imagined.
Sorry,
Yep.
sorry,
Mhm.
can you just rephrase this?
Yep.
Two-time probabilities, now you use this G-twirl, use the.
To construct these observables, yes, you can show that, which is the quantization of this perturbative expansion of these. Yeah, and then this is just the standard conditional probability formula.
So what was he doing wrong?
He was not using, when you go to what he was doing, You can. These here, basically, after you do this, you're out of the physical Hilbert space. And then you're computing things that are no longer gauge invariant because you don't have the physical state after this. But if you replace these with appropriate complete observables that are gauge invariant, you stay within the physical Hilbert space. Okay, and then just to satisfy Don as well, you can do what Kukash imagined, but you can also incorporate memories into the Hamiltonian constraint. So basically the idea is maybe you have your clock, this is kind of getting to what you mentioned, is you couple the system to a memory or a register or an auxiliary system at some time t1. So you modify your constraint so that there's this is the physical mechanism,
Yeah.
where you have this coupling between the system and this apparatus or memory at time A. And it only turns on at time t1. And you can do the same thing at t2. And then you can ask, this conditional probability becomes, what's the probability of A and B, these registers reading particular outcomes at the time t2? And then you recover the correct propagator in this case as well too. So in this way, in some sense, if those of you are familiar with the idea of the Heisenberg cut in quantum mechanics, I think what these folks did is they really incorporated the theory of measurement in Hamiltonian constraints and moved the Heisenberg cut to having some actual apparatus that's recording the particular outcome. Sorry, did you?
Yeah, I just want to confirm when you're saying the memory.
Yes.
Do you mean specific quantum effect or just the idea of causality as a whole?
I just mean some other auxiliary system that's described by a Hilbert space that could store, it could be like L2 of R or some other Hilbert space that records the measurement outcome of the system.
I would just avoiding a classical memory just because you don't want to use a classical because you can just record it in a sheet of paper.
Sure, and I could write down a Hilbert space for the sheet of paper, and I could
Something
about
that
different
flips,
states.
for example.
Yeah. It could be a qubit. And,
Yeah.
yeah.
Alison, I do want to know, can you, how many measurements can you make?
Oh, you can generalize this to as many as you want.
So it could be the discrete measurements, or number of discrete, not continuous time.
Yeah, so in sense, I mean, if you wanted, you could replace these delta functions with some Gaussian and have it spread out. You could do that. I don't know if folks have looked at that yet.
Yeah, so could it in some sense be a continuous measurement of time or more by approximation, making measurements?
That I don't know off the top of my head, because it may modify the dynamics if you keep measuring.
Oh, yeah.
But I don't, I don't know if the.
Yeah.
Okay. All right, so good. I have 19 minutes left. So maybe I just briefly explain some generalizations of this formalism I've worked out. Hopefully now I've convinced you that that this relational approach using covariant POVMs is interesting, and I've explained the way to cover a notion of dynamics from a Hamiltonian constraint. I want to talk about two generalizations. The first is what happens when we have this interaction term here in our Hamiltonian constraint. How does that change things? Okay, and this is something we would have to confront if we wanted to apply this to full general relativity, because there is an interaction term there. So again, I can define my clock states as before and associate them with the covariant POVM. I can define a conditional state, and then I can ask, what is the differential equation that this satisfies? And I now have some interaction between them. And you get something that looks like this. So we call this the modified Schrodinger equation. You can see if you turn the interaction off, this term goes away, and you just get the usual Schrodinger equation. But now what you get is the Schrodinger equation becomes this integral differential equation with this kernel that depends on the interaction. Yeah, it's non-local in time in the sense that the time derivative here at some time t depends on the entire history. This is an integral over all t. So that's maybe a little strange. And the other odd thing is that for certain types of interactions, this describes a non-unitary evolution. There's certain conditions on the interaction Hamiltonian that have to be satisfied. So just as an example, maybe you have gravity in the sense that I have a Newtonian gravity that has a Hamiltonian, something like this, that couples the clock in the system. So I'm just replacing the mass in the Newtonian potential with the Hamiltonians of the clock in the system. And you can work out what this Schrodinger equation is. And in this case, you do get a unitary evolution. And the system Hamiltonian gets corrections that depend on that interaction.
Can you obtain a measurement on how non-unitary heat, how
Yeah,
you know what I mean?
yeah, a measure of how, yes.
How non-unitary it is?
Yeah, so you can write down the condition for a certain expression to vanish, and that'll guarantee that it's unitary. So I imagine how far away that is from zero or being non-unitary. I can show you this in the
Very nice.
paper. Yeah. Okay, what about field theory? So if you look back at Don Page's original papers, he was actually interested in applying this to full quantum gravity and quantum field theory. So maybe I say a few words about this. It says many of the ideas in this paper have been expressed before, particularly in the context of quantum gravity, where after much initial confusion has now been recognized that observable time can only be defined intrinsically. Right? This goes right back to the early days of quantum gravity. However, it was not generally been recognized that the same concepts also apply in quantum field theory, in flat space-time, or even in non-relativistic quantum. I wrote a follow-up note as well. He says, for simplicity, one can think of the rest of the system as a particle with position. That's kind of the idea we've been talking about, which is a convenient model to have in mind. But my discussion is not intended to be limited to such a simple model. For example, a closed system could consist of relativistic quantum fields within the given classical background space-time. And so with my colleagues, this is the generalization I just want to show briefly that we did. And we worked with something called parameterized field theory. And so the idea is you start with some action for your scalar field, okay, something like this expression here. And then just how we did with the free particle, where we reparameterized the time coordinate, included explicitly the time coordinate in our Lagrangian, so it's treated dynamically. You can reparameterize this action and promote the t and the x to dynamical fields or embedding fields. And so you get an action that now just depends on the scalar field phi, and these embedding fields that correspond to different hypersurfaces in a classical background space. And so this was first studied by Kukash and then others, Ashtekar, Lewandowski, it's in Kiefer's book as well too. So the idea is that these embedding fields, x mu, are going to define a foliation of the Minkowski space in this case.
And that is like a view evolution?
No. This L is just a Lagrangian, just a Lagrangian.
Okay.
Yeah. For your scalar field. So, okay, what can you do? How might you quantize this? Well, the idea here is to define a coordinate operator and these embedding states. So analogous to clock states, instead of having a state that corresponds to a clock reading a particular instant of time, we're going to have a state of the embedding fields that corresponds to a particular leaf in a foliation of the space-time. So when you act on it with this coordinate operator, you get back the appropriate coordinate function. Right? And then you can talk about its conjugate momentum, pi mu, that's canonically conjugate to it. And if you carry out the canonical analysis, you get a Hamiltonian constraint that looks similar to what we've been talking about before. You have these momentum, instead of this momentum being conjugate to the clock, you have the momentum conjugate to this coordinate field operator. And then you have this Hamiltonian density, that's the Hamiltonian density for the scalar field. And in the quantization, Kukash works this all out. You pick up an anomaly as well. So, and then here's the stress tensor. So, okay, you can proceed in an analogous way. You can define coherent states relative to a subgroup of the diffeomorphism group on Minkowski space. So basically, what this is doing is you take some initial embedding, analogous to the initial state of your clock, and you act on it by a unitary representation of this group. And what does that do? That generates another embedding labeled by V and S. which basically takes you from some initial embedding to some other embedding here. So this is the analogous covariance property that I showed for clocks, except now it's being applied to embedding fields. If you work out what the conditional state is now by conditioning the physical state on one in which the embedding fields take a particular configuration, you now get a functional that depends on which embedding you're talking about. And then you can ask, how does this state change when I change that embedding? And I get a functional differential equation known as the Schwinger-Tominaga equation. This was really exciting because this is, an application of this Page-Wouters formalism to relativistic quantum field theory, something that Don Page wanted to do all the way back in the 80s. So here you can integrate this and get a Hamiltonian along a particular foliation and get a Hamiltonian. But here, instead of the state changing in time, we have a functional that can vary with the definition of the embedding or the hypersurface that it's on. Okay, good. All right, I think I have. You guys are all still with me. I don't know. I've said a lot to 10 minutes. Okay. So this is so okay. If you're just waking up, welcome. But this is a little bit different, but using the same formalism to actually try and talk about a new effect, right? And what's nice about what Feynman has this quote where he says, any good physicist knows 6 or 7 different formulations of exactly the same physics. Right? And why do we know 6 or 7 different formulations of the same physics? Because they suggest different ideas and different ways to modify them. And so I think this conditional probability, my colleague Mehdi and I, when we first started studying this, we're interested in time dilation and asking conditional probabilities about what different clocks and what times different clocks would read. So the basic setup I'm going to analyze now is, what if we have this clock here, okay, clock A, it's blue, and it's moving in a superposition of 2 different momentum wave packets. And what time is it going to read relative to clock B that's at rest with respect to this background frame? And in particular, is it different than if I just flipped a coin and I prepared the state of clock A half the time, centered around one momentum and the other half around some other time? Is there an effect to the time dilation that the clock would observe because it is in a genuine superposition? So what is this going to be about? No longer are we going to have a deterministic relationship between what the clock reads in one frame to the other. It's going to be a probabilistic relation. And so we're going to be interested in conditional probabilities associated with the proper times read by these clocks. So namely, what's the proper time read by tau A when clock B reads a particular time B? And so this conditional probability formulas are a good formalism to actually compute these. And maybe you're like, okay, how can I put a big clock in a superposition of different speeds? Well, maybe just in the back of your mind, you can imagine the lifetime of an atom. We'll talk a little bit more about that specifically in a bit. So again, I can start with an action for a relativistic particle. What's important about this action is it's the usual action, mc squared, for a particle moving in Minkowski space, but now it carries some internal degrees of freedom that evolve according to the proper time of the particle. And I can carry out the canonical analysis, and I get the usual constraint equation, p squared plus m squared. But this m now is this sum of the mass parameter m plus the internal energy contribution for the internal degrees of freedom that it's carrying. So maybe you imagine this as an atom, okay? It has some center of mass momentum, but then there's some energy associated with the internal electronic energy. Okay, you can, this is a quadratic equation, you can factor this constraint, and you can impose either C plus or C minus these constraints commute. So we can define our physical Hilbert space just by looking at this positive energy sector. And so we get a Hamiltonian constraint that looks something like this. We can define a conditional state analogous to what we've talked about before in the Page-Wouters proposal, and we get a Schrodinger equation as well, this relativistic Schrodinger. But now the idea is going to be to define a proper time observable T that we're going to measure on this system that's covariant with respect to the group generated by the internal clock Hamiltonian. So this is actually going to lead to a proper time observable. So maybe just, yeah.
Sorry, this previous T was not this?
No, this was this background coordinate time. Sorry, yeah. There's these internal degrees of freedom I'm calling C that are these internal clock degrees of freedom. So this is covariant with respect to P naught. Okay. So I want to define a proper time observable that's covariant with respect to this internal clock Hamiltonian. And right away from that uncertainty relation we talked about, and we saw Nadja wrote it on the board the other day, right, about proper time and mass. We get a generalized uncertainty relation between proper time and mass here. So the product of the uncertainty and the proper time and the mass of the clock, this is what you're saying as well too, is going to be greater than h bar over 2c squared. So what I want to emphasize here actually is that, you know, there's this, oh, what's the meaning of the time energy uncertainty relation? There's no time operator. Well, you know, we have the Cramer-Rao bound, which is, you know, a rigorous bound that's built on covariant POVMs or POVMs that are estimating time. So it's well defined. It's not that it has to be sort of postulated ad hoc. This is a rigorous, well defined. I just want
the internal clock, you can use it one time, and then it stops being an internal, use it for the measurements, and then does it continue to be an internal clock?
This is a good question. I think it depends on exactly how you go about measuring it. So when I talk about the POVMs, they only give the probability of the clock reading a particular time. They don't actually tell you what the state is after you make a measurement. So maybe you engineer something, your measurement, where you make a measurement, you get an outcome, and then you prepare it back to an initial state, so it keeps ticking. So you could do this, but that would be an extra description in the measurement. Yeah.
Not like a weak measurement in that sense.
No. Yeah. Okay. So all right, this is the punchline. Is that you can compute what's the probability that I started with clock A reading a particular time tau A, when clock B reads a particular time tau B. And you can suppose that this clock A is moving in a superposition of two different momentum wave packets, weighted by cos theta and sine theta and having a relative phase. And then you can compute the expectation value, the average value that clock of the time that clock A reads. Okay, these are these internal clocks measuring proper time. And then you get something that looks like this expression here. So I have it up here again. And there's two terms. The first is this gamma C, which is just a mixture of the classical time dilation you would expect to see from the clock if it was moving at either P bar A or P bar A prime. This is the classical contribution. And then this is the quantum contribution that depends on the relative phase phi. Okay, so it's a little bit messy here. I'll make a plot on the next slide, but the point is that the average time seen by clock A now picks up this part that depends on the coherence between these two wave packets. So what does this gamma Q look like? Well, I'm plotting it here as a function of the separation of those momentum wave packets in momentum space. And what you see is, okay, when they exactly overlap, there's no superposition anymore. So this gamma Q goes away. And when they're really far apart in momentum space, it also goes away. So there's some optimal difference in the separation of the momentum wave packets that maximizes this gamma Q. And then the other important thing is it depends on this relative phase phi. So this is a genuine quantum effect. So, okay, so there's this gamma Q. Do we have any hope of actually seeing it in an experiment? So what I did with my colleagues in Warsaw is we considered an atom and we talked about measuring its lifetime. Right? So you can imagine a two-level atom that's coupled to the electromagnetic field. And so then it decays from its excited state, and you can ask, what's its lifetime? Right? That's going to experience time dilation. So you can do an honest quantum optics computation. These are the Hamiltonians of the atom, and the electromagnetic field and the coupling. So I won't go into detail, but the point is, you can look at the spontaneous emission rate, and you can compare the spontaneous emission rate of these wave packets in a classical mixture versus this superposition state, and you find that you get exactly the gamma Q inverse that I had shown before. Yeah, so this suggests here we're looking at a very concrete different clock model. What I showed originally was for an idealized simple clock. This is, the lifetime of an atom or the spontaneous emission rate, and you get the same thing. And you also get modifications to the line shape as well due to this coherence. So the question is this actually going to be observable in an experiment? I'll say the following. We've seen time dilation observed for clocks moving on the order of several meters per second. And we've created momentum superpositions of particles separated by also several meters per second. So if you use these two very different numbers from these two different state-of-the-art experiments, you get something like this gamma Q inverse is on the order of 10 to the minus 15. And if you are able to maintain the coherence or the superposition of that state for a long enough time, for on the order of, say, a second or less even, which is possible, then this effect, this gamma Q, would be in the current resolution of atomic clocks. But I don't want to say we can just go out and measure it, because these are two very different experiments. One is creating this momentum superposition, and then the other is actually like measuring time and emission rates. So if you can combine these in some clever way, then maybe there's a chance. One idea in the last 2 minutes, sorry, is this is how a typical atomic clock works. Is we have some oven and we prepare some atoms in the ground state, and then we try to excite them by illuminating them with some electromagnetic radiation. And then we have some detector here, and we count how successful we were at tuning that frequency of that light so that it was resonant with the transition we're interested in. And this is, if these are moving with some momentum, it's going to see this radiation red-shifted or blue-shifted. And so in this way, you would be able to experience or witness time dilation for these atoms moving. But what you might do is insert a momentum beam splitter here, where it pairs them moving in this momentum superposition, and then try to illuminate both branches simultaneously. And then this redshift would be dependent on this energy. So maybe this is just a proof of principle of a toy model of an experiment that might actually be able to be done. So, okay, I know you can also do it with gravitational time. But I know I've said a lot, so maybe I'll just zoom out and give a quick summary. I started this talk by talking about what is a clock and how do we measure time in quantum mechanics. And the big idea there is we have to appeal to a more general notion of an observable, namely that of a covariant POVM. Okay. I then showed you how to use these covariant POVMs to talk about relational quantum dynamics. The idea there is we have this Hamiltonian constraint, and we're trying to recover an internal time and ask how the rest of the system looks like with respect to that clock. And you can do that for a wide variety of systems using these covariant POVMs. I talked about two generalizations, this interacting clocks and field theory, and then I used the formalism to talk about this quantum time dilation. So with that, I'll end there. I'm happy to take questions. Thank you.